Hi everybody, today we are going to talk about matrices and using them to solve systems of equations. So just a few basics of matrices. A matrix is simply a rectangular array of numbers, so they look like this. So one thing that it's important to be able to do is to determine the dimension of a matrix. So it's really important to note that we always define the dimension by first stating the number of rows and then columns. So if a matrix has m rows and n columns, we call it an m by n matrix. If a matrix only has one row, we call it a row matrix. If it only has one column, we call it a column matrix. And of course, you guys know rows go across, columns go down. So if I look at this first one, I have one row and one column. So this is just a 1 by 1 matrix. Here I have one row, but 4 columns. So this is a 1 by 4 matrix. Here I have 2 rows and 2 columns, so it's a 2 by 2 matrix. And here, if you count, we have 1, 2, 3 rows and 2 columns. So it's a 3 by 2 matrix. So the application that we're going to use today for matrices is solving a system of equations. So if you have a system that looks like this, you can write it as a matrix in 2 different ways. One is called an augmented matrix, and essentially it includes the constants, and one is called a coefficient matrix, so it only includes the coefficients of your variables. But if you notice, you're literally just taking each coefficient and you're writing it across the rows. So that's how you translate a system of equations into a matrix. And the ones we're going to be working with today are these augmented ones. We want the constant column as well. So when we're solving system of equations, there's 3 main row operations that we're going to use. So it's going to be important that you know how to write the notation, because that's going to be how you show your work and you explain each step. So the first thing you can do is you can actually interchange 2 rows. You can literally swap like the first and third row, and you can show it in this way. You can also multiply a row by a non-zero constant, which is something that we've done when solving systems of equations. So remember, we would multiply an equation by 2, so maybe one of the variables could cancel out. And then another thing that you can do is you can multiply a row, add a multiple of a row to another row. So this is really, really common or very similar to what we did when we were solving systems using elimination, right? We would multiply an equation by -2 and add it to a different equation, so our x's or our y's or our z's would cancel out. So this is how you notate it. All right, so this slide could look very, very overwhelming, but don't panic. It's not as crazy as it looks. So essentially, when we are solving a system of equations using a matrix, our goal is to create what's called row echelon form. So these are all of the ones that have pink are ones that are in row echelon form. So the rules for row echelon form are, if you have a row that's entirely zeros, it needs to be in the bottom, like you see here. For all other rows, the first non-zero entry is 1, and they call that the leading one. So you guys can see that for this row, it starts with a 1. Here's a 0, but that's okay. The first non-zero is a 1. Here's a 1. If you look over in matrix E, your top row is okay, but here your first non-zero entry is a 2, so it's not in row echelon form. Then it says for successive rows, the leading one in the higher row is farther left than the leading one in the lower row. So you can see here, this one is farther left than this one, which is farther left than this one. It doesn't have to go in a perfect step formation like this. You can have something like this where you have a 1 and then you have 2 zeros and a 1, as long as this one is farther to the right. But most of the time, it's going to end up looking something like this, where you have a nice little step or something like this. So this is our goal. We try to create a matrix that is in this row echelon form, and we use that by the process called Gaussian elimination. So it's pretty much a combination of interchanging rows, multiplying them by constants, or adding multiples to other rows. Once we have our matrix in row echelon form, we have 2 options. So there's back substitution, and then there's another process called Gauss-Jordan elimination, but both of those are just kind of the last finishing steps to finish solving for all of your variables. So we'll go over both of those today. Okay, so here's the first example, and let's start by writing this straight as an augmented matrix. So remember, we're just essentially going to list all of our coefficients. So we have 1, -2, 3, and 9, -1, 3, 0, and -4, and 2, -5, 5, and 17. So remember, our first column represents x, then y, then z, and then our constants. So when I look at this, I'm already a little happy because I see that our first term up here is a 1. So we don't need to do any work to change our first row. So then I look down here and I say, okay, I want to turn this term into a 0. And I can think, okay, do I multiply? Do I add? So I notice that if I simply add row 1 and row 2, this term will turn to a 0. So here's how you show that. So we know that our first row is going to stay the same. The operation that we're doing is we're going to do R1 plus R2, and we write that new row as a replacement in row 2. So I see that 1 plus -1 is 0. -2 plus 3 is 1, 3 plus 0 is 3, and 9 plus -4 is 5. And then we haven't done anything to our third row yet. So that was actually a really nice step because not only did we create our 0, this next term just happened to be a 1. So actually our second row is complete in our transformation to row echelon form. So now I need to go down to my third row. First thing I'm going to need to focus on is turning this into a 0. Well, I see that if I add this row to row 1 multiplied by -2, I have a -2 and a +2, this will become a 0. So my first two rows will stay the same. And this operation will be -2 times R1, and then I'm going to add it to R3. So I'm going to multiply this by -2, and I'm going to add it here. So this gives us -2 plus 2. So we'll have a 0. And then we'd have 4 plus -5, so we have a -1. And then we'll have -6 plus 5, so we'll have another -1. And then we'll have a -18 plus 17, so we'll have another -1. So our first 0 has been created, but we know that for row echelon form, this also will need to be a 0. So I need to find a way where I can turn this to a 0. And I notice that, oh, if I simply add row 3 and row 2, this term will become a 0. So our first row stays the same, our second row stays the same, and then I'm going to do some addition of row 2 and row 3. So now this is a 0, this is a 0, this is a 2, and this becomes 4. So now I'm almost done, but I know that I need to create that leading one. So I need to find some way to turn this into a 1. And typically when we have something like this, and we're just trying to change this last term to a 1, we're not going to be adding it to anything because we're not trying to eliminate it. We can actually multiply this row by the reciprocal, by 1/2, and that will turn that 2 into a 1. So I'm going to rewrite the first 2. Okay, and then my step would be written as 1/2 R3. So that we get 0, 0, 2 times 1/2 is 1, and 4 times 1/2 is 2. So now our matrix is in row echelon form. And I can see that because I have the 1, 0, 1, 0, 0, 1. So now I'm going to take our matrix and rewrite it back as a system of equations. So that first row says x minus 2y plus 3z equals 9. And then we have 1y plus 3z equals 5. And then we just have z equals 2. So now we can start the process of back substitution. So we essentially take this and we plug it in here, and when we do that, we can see that y is -1, and then we can take our y and our z values and we can plug it in here, and we see that x equals +1. And then all you need to do is write it as a coordinate, and you're done. So like we mentioned, this last step that we did here of rewriting it as a system of equations and then back substituting, that's just one option. We'll talk about our second option in a couple of slides. All right, so I want to do one more example together. So once again, let's start by writing this as a matrix, an augmented matrix. So let's list the coefficients. Okay. So remember, we have some options of what we can do to our matrix. So if you're strategic, you can definitely do steps at the beginning to make it easier. So I notice that here I have a row that starts with a 0. And I notice that here I have a row that starts with a 1. And we know that we always like our top row to have that 1 in the upper left-hand corner. And we actually like our second row to start with a 0. So I notice that if I actually swap or interchange rows 1 and 2, I have a much better matrix to work with. So that's actually going to be our first step there. We're just going to interchange rows 1 and 2. Rows 3 and 4 are going to stay the same. And the way that you can show that step is you can say R2, and then you can draw your double arrow, and then R1, showing that they have been replaced. So here, this is actually really nice. Row 1, we're happy with. Row 2, it says 0, 1, so we're happy with row 2 as well. So now I need to find some ways to work with row 3 and 4. So something you can start doing as you become more comfortable with working with matrices is doing multiple steps in one. So I'm going to see if we can do 2 steps in one here. If I want us to turn this number into a 0 and this number into a 0. So I know that if I add this equation to, this row to row 1 times -2, it will cancel out. And I know if I add this row to row 1 times -1, it will cancel out. So we're going to do both of those steps in the same jump. So I'm going to start by rewriting our first row. So 1, 2, -1, 0, 2. Then we have 0, 1, 1, -2, and -3. So remember, in row 3, we are going to do -2 times row 1, and we're going to add it to row 3. So that will become 0, 0, 3, -3, and -6. And then down in row 4, we're going to do negative row 1 plus row 4, because that will cancel out our x term. So here we get 0, -6, -6, -1, and -21. Okay, that actually worked out really nicely, because not only did our first term here become a 0, but this one also did. So now I look at this and I see, okay, I'm going to need to create some zeros here, and I'm going to need to turn this into a 1. So let's start by fixing our bottom row. I want to turn this into a 0. So I see that I can do this, turn this to a 0 by adding it to 6 times row 2. So let's do that. So 6 times, we're working with the 4th row. So we'll do 6 times row 2, and we'll add it to our row 4. And this is actually a pretty nice step because not only does this become 0, this becomes 0, and this becomes -13 and -39, which are both divisible by 13. So they're pretty nice numbers to work with. So now I can see that the last things that I need to fix, well, I need to find some way to turn this into a 1 and some way to turn that into a 1. So this is where we're going to multiply by a constant. We're actually going to multiply by the reciprocal of those numbers. So let's set up our first 2 rows. And then this row I'm going to multiply by 1/3. So we have 1/3 row 3. So we end up with 0, 0, 1, -1, and -2. And then for our 4th row, I'm going to multiply it by -1/13, which will turn that number into a 1, times row 4. So 0, 0, 0, 1, and then +3. Okay, so now I have my matrix in row echelon form, which means that now I can back substitute. So I'm going to take my matrix and rewrite it as a system of equations. So x plus 2y minus z equals 2, y plus z minus 2w equals -3, z minus w equals -2, and w equals 3. And then I kind of just start working my way up. So if I substitute this in here, we get z equals 1. And I could substitute that in here, and we get y equals 2. And then we can substitute up to here, and we get x equals -1. So our final solution is -1, 2, 1, 3. All right, so at this point, I'd like you to pause the video and give this problem a try. Oh, I would like to give you guys a hint. So you need to be careful when you're doing your first step, because if you approach it the wrong way, it can get really messy. We know that we want to turn this number into a 1. However, if you go and you multiply this number by 1/-3, you're going to get some really ugly fractions. So see if there's a better way you can do that. And the hint I'm going to give you is that you should add row 1 to row 3, and that will give you a 1 right here. Okay, so we're going to start going through the steps. So as I mentioned, for that first step, if you add row 1 and row 3, you get a nice 1 up in the upper left-hand corner, which is exactly what we want. From there, we can add row 2 and -3 times row 1 to get our 0, and we can add row 3 and -4 times row 1 to get our 0, which works out really nicely in row 2 because we have all 13, so it's nice when they're all divisible by the same thing. So then we know that our goal is to turn this into a 1, and we can do that by multiplying row 2 by 1/13. And then we know that we need to keep working through our bottom row. So I can turn this term into a 0 by adding it to -4 times row 2. And then I can turn this term into a 1 by multiplying this row by 1/2. From there, I can use back substitution. And I know that z is 1, plug it in here, y is -2, plug those in up here, and you get x equals 4. So if you need to look at all the steps again, you should be able to follow these steps, and you should be able to fix your matrices if something went wrong along the way. All right, so now I want to show you a different way to finish solving these. So this is actually the exact example, or the exact system from example 1. So I'm jumping down to the part where we have it in row echelon form. So when we did this, so this is what we got. So from here, when we were doing example 1, we used back substitution. Now I wanted to show you guys a different way to finish it, which is called Gauss, sorry, there's 2 S's there, Gauss-Jordan elimination. So the main idea here is once we have our matrix in row echelon form, we want to go one step farther and see if we can turn this to 0, this to 0, and this to 0. The idea is if we can create zeros on this side of our diagonal as well, we actually will have our answer. We have 1x equals some constant, 1y equals a constant, and 1z equals a constant. So all of the other variables in each row are gone. So we're going to use the same elementary row operations of adding or multiplying by a constant to see if we can turn these into zeros. So the first thing that I see that we can do is I know that we can turn this into a 0 by adding it to 2 times row 2. If I multiply row 2 by 2, these will cancel out. So that can be our first step. So this will stay the same. This will stay the same. And here, we're going to say 2 times row 2 plus row 1. So it works out really nicely because this 0 will not change our 1. We don't want to change our 1s or any of the zeros that we already have because that would be working backwards. So this is unchanged. This becomes 0. This becomes a 9, and this becomes a 19. So we still need to work through and see if we can find some way to change those 2 terms into zeros as well. So let's set up our next matrix. So I can see that I can turn this into a 0 by adding row 1 to -9 times row 3, because this will become -9 and this will become +9, and they'll cancel out. And these zeros won't change any of these, which is what we want. So that will give us 1, 0, 0, and a 1. And then I can see that I can turn this term to a 0 by adding it to -3 times row 3. Plus our 2, so that will give us a 0, a 1, a 0, and then a -1. And then our bottom row was already good. And now we have this Gauss-Jordan elimination set up. So remember, it doesn't matter what your constants are. We don't care about this. They can be anything. Your variables can be equal to whatever you want. This is the setup we're looking for. Everything else is 0 except for 1 variable per row. So now we actually have our answers because that first row tells us that x equals 1. The second row tells us that y is -1, and then z is 2. So we're done. So remember, this is just a different way to finish solving your problem. You still need to put your matrix into into row echelon form, but then instead of using back substitution, you can create more zeros, which is called that Gauss-Jordan elimination method. All right, so go ahead and pause the video and give this problem a try. First, put it into row echelon, and please finish solving using Gauss-Jordan. Okay, so first thing I did here is I noticed that if I add rows 1 and row 3, that will give me a -1 here. So then I multiply it by -1 after, giving me my 1 in the upper left. So you can do that in 2 steps. I kind of just combined 2 steps. And then I turned this term and this term to 0 by adding it with a multiple of row 1. So I did 5 times row 1 plus row 2, -2 times row 1 plus row 3. So I created my zeros here. And then in my next step, I multiplied row 2 by -1/22 to turn this term into a 0. And then I focused my attention on the third row. So I know that this needs to become a 0. So we did -8 times row 2 plus row 3. So they cancel out and this becomes a 0. And then from there, we just need to make sure that this last term becomes 1. So I can achieve that by multiplying this row by -1/5. And here's what I get. Now remember from here, now our matrix is in row echelon form, but we want to finish solving this one using Gauss-Jordan elimination. So I'm going to start by trying to create a 0 here, which you can do by adding row 1 plus 5 times row 2. And then remember, we want to create a 0 here as well. So we can add R1 and the opposite of R3, and that will become a 0. So once you have a setup like this, we actually have our answer. X equals 7, Y, or 1Y equals 4, and 1Z equals -3. So there's our solution. So just remember that you do need to be strategic with these types of problems. So for example, if you're trying to create a 1 in this corner, I probably would not multiply this equation by 1/2. You're going to get ugly fractions. What I would do is I would add it to row 3 and then multiply it by -1. So just be strategic, and if you notice that your problem is very quickly getting very ugly, I would stop and try a different path. Okay, now we're going to look at what a system with no solution looks like when solving with matrices. So let's set up our augmented matrix. Okay, so we already have our 1 here. Let's create some zeros. So I'm going to try to turn all 3 of these to zeros in one step. So let's see if we can do that. Our first row is okay. So for my second row, if I add -R1 and R2, they should cancel out. For my third row, if I add -2 times R1 plus R3, that will give me a -2 here and a +2 here. And then for our fourth row, we have to do -3 R1 plus R4. So that gives us -3 and +3. And when we do that, we get something that looks like this. So we'll get 0, 1, -1, 2, 0, -1, +1, -4, and 0, 5, -7, and -11. Now, if you're not comfortable doing multiple steps in one jump, then just write it out as 3 different steps. That's totally fine. Okay, so from here I see row 1 is good. Row 2 is actually good because I have the 0 and then my 1. Then I see, okay, I need to turn this into a 0. And I see that I can do that by adding it to row 2. So I'm going to do that. So my first 2 rows stay the same. And then I'm going to do R2 plus R3. So that gives us 0, 0, 0, -2. So this is where you kind of just need to remember what your matrix is actually representing. If you look at this row, if you look at this row right here, and if we rewrite that back as an equation, we have 0x plus 0y plus 0z. So it says 0 equals -2. So this is really common. It looks just like the no solution problems when we solved using systems of equations. If you end up with an equation that is just simply not true, like 0 equals -2, that's how you know that it is no solution. So that's just something to look out for. But like I said, it looks very similar to the no solution problems when we were solving with equations. So it should look pretty familiar. Okay, so the last kind of interesting case that I want to talk about is what it looks like to have an infinite number of solutions and then how we're going to write it. So let's start by creating our matrix. Okay, so let's start by creating a 1 right here. I notice that all 3 of these terms are multiples of 2. So rather than maybe adding it to the opposite of that and then multiplying by -1, I see I can really easily multiply by 1/2 and I will still get a very, very nice row. So sometimes, depending on what the coefficients are, you can definitely do that from the get-go. So here that will just give us 1, 2, -1, and 0. And then we have 3, 5, 0, and 1. Okay, and so now I know that our next goal would be to create a 0 right here. So I can do that by adding it to -3 times row 1. So our first row will stay the same. And then here we'll do -3 times row 1 plus row 2. So we have 0, -1, 3, and 1. Okay, so now I want to go as far as I can, and I know that this really needs to be a positive 1. So I'm just going to multiply my second row by -1. So -R2. Okay, so technically this is in row echelon form, but you might notice that we can't completely solve for any of our variables. So what we can do, so this is kind of an interesting case, is we can try to create another 0 up here. So when you have this case, we're going to try to turn this into a 0. The idea is like we're trying to eliminate another variable. Here we've eliminated one variable. Here we could either eliminate one of these two. So let's see if we can eliminate this 2. So I see that I can do that by doing -2 times row 2 plus R1. And you'll see why this is useful in just a second. So that will become 1, 0, 5, 2, and then our second row stays the same. So this is nice because here I have just a system of X and Z, and here I have just a system of Y and Z, so it makes it a little bit easier to finish solving. So this will have infinite solutions, but we still need to find a way to write it. So let's translate these back into equations. And this is when we're going to set one of our variables equal to A. So I think in this case, it might be easiest to say, okay, let Z equal A. So if we do that, we can say X plus 5A equals 2. So X is equal to -5A plus 2. Then I can substitute my new Z value into my second equation. So Y minus 3A equals -1. So Y equals 3A minus 1. So remember, our goal here is just to write every term in terms of a new variable, which we usually pick to be A. And then we can still write it as an ordered triple. So I also would like to remind you that you don't necessarily have to set Z equal to A, but in this case, it's definitely the easiest way to go because I can really easily write X in terms of it and Y in terms of it. So if you initially pick something else and you start noticing that your answers are really messy, try setting something else equal to A, and I think it'll be much easier to work with. All right, that is all for today. Thank you so much for watching.